Assalamualaikum and a very good day I bid to all fellow audience. So first and foremost, I would like to welcome all of you to the Advances in Geophysics webinar series, in which this special webinar is organized by Geological Society of Malaysia in collaboration with the Center of Seismic Imaging UTP. So for today's webinar series, it's actually our 10th webinar series and will be mainly related to the earthquakes and geothermal resources of Malay Peninsula. And so before I pass today's session to our honorable speaker, allow me to briefly share with you the background of our speakers. The Associate Professor Dr. Helmut Duras is an accomplished scientist with extensive experience in the field of geophysics and geothermal energy. He is a German national and currently holds the position of Associate Professor at the Geophysics Research Center, Division of Physical Science, Faculty of Science, Prince of Songkhla University, Hat Yai, Thailand. Dr. Duras has been a lecturer and researcher in various universities in Thailand since the year 2000. He started his academic career as a lecturer and researcher at Suranari University of Technology, Thailand, where he served from 2000 to 2003. He then moved to Mahidol University, Thailand, where he worked as a lecturer and researcher in 2004 before joining Prince of Songkhla University, where he has been a lecturer and researcher since 2004. Dr. Duras received his PhD in Natural Sciences from the University of Göttingen, Germany in 1997. Prior to his doctoral studies, he completed his postdoc from 1998 to 2000. Dr. Duras has also made significant contributions to the field of geophysics and geothermal energy. His research work on geothermal energy utilization and its potential in southern Thailand has been widely published in reputable scientific journals. Some of his recent publications include geochemical characterization of hot spring waters from southern Thailand as the base for geothermal energy utilization, geothermal resources in southern Thailand, part of a renewable energy mix, and geological setting and hydrogeothermal characteristics of the Kapong non-volcanic hot spring area in southern Thailand. As an assistant professor at Prince of Songkhla University, Dr. Duras is also actively involved in teaching and supervising graduate students. He is also a member of several professional societies, which include the American Geophysical Union and also the European Geosciences Union. And so now, without further ado, I would like to invite Associate Professor Dr. Helmut Duras to deliver his talk on the earthquakes and geothermal resources of the Malay Peninsula. Please welcome, Doctor.
Yeah, thank you very much. So, good afternoon again, and thank you very much for the introduction. Today we'll talk a little bit more about our area here in Malay Peninsula in terms of earthquakes and geothermal resources. Where are we? I know everybody, no? We know where we are, no? Here along the peninsula. From the north here is Bangkok, to the south to Singapore, crossing Thailand, Malaysia and Singapore. So what is the special or certain on this area? When we go back, you can see here is actually the topography of the Andaman Sea, and this is actually our subduction zone. Which is having a certain effect, and I will show this over the coming minutes. You are also familiar with these pictures where we map here in our subduction zone with the triangles, but also we have a lot of volcanoes in the single triangles here and our strike-slip fault, as well as we have an extensional basin here in the Andaman Sea. So for interest, we have actually almost all three major plate boundaries here in a very confined area. Plate is moving, you are familiar with this too, subducting under the Eurasian plate with about 7 centimeters per year. Still going on. A cross section, just for the basics, that where we expect the earthquakes, because one of our topics is the earthquake. So we have earthquakes here in the shallow part of the subduction zone. We have deeper earthquakes along the subducting slab, and we have also along the fault zones and also volcano-related earthquakes. No? In Indonesia, the Merapi is just active again. And if we look again a little bit an overview, we have our Eurasian plate, Sunda plate here. Then we have our Australian plate, and probably we are separating this into the Indian plate. And here is our small Myanmar or Burma plate. And these are major sources of regional earthquakes, the subduction zone for sure, the fault zone, the plate boundaries, and the volcanic arc, things we have seen before. So what about earthquakes here? Do we have to concern about earthquakes? If you look back, we are here in southern Thailand, West Malaysia. Do we have to concern about earthquakes? For sure, yes. Because some of you might not remember in person the 2004, December 26 earthquake with a magnitude somewhere between 9.1 and 9.3. But I remember more precisely the tsunami. Because the tsunami came at all the beaches here in the Andaman Sea, which is not my topic today. Here's Hat Yai, where I am located. You see, we are about 600 kilometers from the subduction zone, about 600, yeah, a little bit more than 600 kilometers. And if we look at our data we acquired on that day, on 26th of December, this is the earthquake from our station at our university. You can see here, this is the origin of the earthquake at our university at a little bit after 8 a.m. Thai time. The origin here is about 7:58:53 in the morning, arriving about 1.5 minutes later in Hat Yai, traveling about 660 kilometers on the surface distance. Did we have to concern about that? Yes, some newspaper here from 2004. One day later here that we feel the strong vibration. Also, we have some small things happening. So as a geophysicist, we wanted to find out what is the intensity. And this is part of earthquake investigation. What is the intensity here in Hat Yai? This is a map of Hat Yai city. Here's our university on the right side. And we did a lot of questionnaire, about 75 for the intensity analysis, with more than 64 from the ground, and also people in high-rise building contributed to that. So what did we learn from that? We divided all the city area in 4 zones because of the possibility of different subsurface conditions in terms of geology, sand, maybe along the river beds. We didn't know at that time, we have no idea about the subsurface conditions. My colleague is working on that now. So we divided that zone, and what we get after we did all the questionnaire and applied the European macroseismic scale we finally get an intensity of 6 in all the zones. So we combined it to an intensity of 6. If we compare that to the US Geological Survey on the modified Macaulay, we see they get a 5. No, we also would get a 6 on the modified Macaulay, although we use the EMS, the European Macroseismic Scale. Intensity 6 is something important for the building design, for the building structure, because the next earthquake can come again. So this is one of the motivations. We studied this earthquake and the effects of the earthquake. And now let us come to the region. First of all, a little bit looking at the tectonics here in southern Thailand and in western Malaysia. Without going into the different rock types, we see major fault zone here, the Ranong AFZ Ranong fault zone and the Klong Maril fault zone here in KMFZ. And here also in western Malaysia, here especially the Bukit Tinggi fault zone here and also the Kuala Lumpur fault zone. But also here, other fault zone here, Kela, Karak and Lepri here, mostly north-south. The other one is a little bit northwest-southeast. And we measured earthquakes, especially in Thailand, by ourselves. And we looked at data collected from other networks around the area in order to see what is the seismicity. A little bit a short note. If I go back, and also a little bit of motivation, because this big fault zone, these larger fault zones, which are morphologically easy to see and geologically easy to identify, were considered non-active before 2004. Because not really earthquakes have associated with this fault. So the overall understanding in the geoscience community was it is a non-active fault. And there, shortly after, in late 2004, and we measured earthquakes together with our geological survey in Thailand. And we measured a number of earthquakes I will show you later. Here, again, the seismic station. We also got data from after 2004, also in Malaysia and southern Thailand. We have to know that in some time after 2004, it took maybe 5 years that the network of seismic station was upgraded in both countries before most the common understanding was mostly that we have relatively low to no seismicity in our peninsula. We also looked a little bit on pre-instrumental data. I will show you a few things. So an overview of the data we considered in southern Thailand and western Malaysia from different data sets and different networks over different period of time. And you can see already that the numbers in Thailand are quite higher than in Malaysia. You see the numbers in Malaysia are relatively low in terms of seismicity. However, we still have earthquakes. I will show you a short picture, a photo and a short setup of our seismic station here in Phang Na, which is in north of Phuket in western part of southern Thailand. with our seismometer on the hard rock base, with a seismograph and the extra wooden hut with a GPS antenna and a continuous power line. We operated this for a couple of months after the 2004 earthquake. And later, a few years later, also we did some further measurements. Here, a short graph of one of the earthquakes here, which occurred in March 2005 here with different stations. You can identify the P wave, the primary or the compressional wave here, the shear wave, the S wave in all three seismic stations. Here's a set component in order to find the location. Before I go further into the earthquakes, we also identified events at events at similar daytime. Here I just show we have about 37 events, and the daytime here in UTC is almost the same. And not only the time was similar, but also the location was similar. In a very short time range. And we identified this as blasting. Because in the area where we set up our seismometers, also a lot of active quarries, limestone, where they did blasting in order to mining the rock, which is considerably hard, especially the dolomitic limestone. And also we could identify the time was, although at certain times, not at weekends, not on holidays, also that we are clear that was a blasting event from man-made. So these things you also find in the seismic records, and here again from the blasting, here also from two stations, the set component, you can see here is a first P wave arrival and the shear wave arrival. We have also considerably a surface wave here, Rayleigh wave. And you can see also that the delta time between the P and S wave arrival here, in both cases, they are very close to the seismic station. The delta time between the P and S wave arrival needed for identifying the distance is relatively short. Coming back to our main earthquakes, and a little bit about the methodology, looking at all the data here. We also reanalyzed existing data we had in our catalog, in our database, and try to produce a catalog, an updated catalog and seismic maps in order to do the analysis. I will show you some of the data. So here, a little bit from the reprocessing of the data, we are using the Sisan software from southern Thailand on the left, here from western Malaysia here on the right side, in order to determine again origin time, location, focal depth and magnitude. There's a lot of issues in terms of data processing which we need to be considered in terms of velocity model. We are using the Jasper 91, but this is not necessarily the truth for our southern peninsula here, or southern Thailand and Malaysia. But we know that the Moho is roughly at the depth here of about 35 kilometer, at least in Thailand. And there's definitely uncertainties in picking the phases, in looking at the station data, usually the closer station data are better. As I said, for the velocity, we cannot do much if we don't have any velocity model specifically for the area. So in the future, maybe we need to reprocess again if we get a better velocity model. We also looked into pre-instrumental seismicity, especially in southern Thailand, where we did paleoseismological studies by ourselves and also by some other people. In Western Malaysia, we also had some paleoseismological studies and also historical earthquakes, which are not really available, where the seismograph, the waveforms are not really available. Here in Thailand, for example, we have quite a number of earthquake observations before 2004, but they are also quite limited. Because, as I said, at the beginning, until I would say 2004, southern Thailand, in northern Thailand is a little bit different. We have earthquakes, but southern Thailand, and I believe also Western Malaysia, was considered really not really seismic active or seismicity areas. So now let us look at the results, what we have for southern Thailand. Here on the left side on our map here in southern Thailand, you can see our fault zones again here in blue, and in yellow color we have the shallow earthquakes, and we have a few deeper earthquakes in blue and purple, here in blue and purple. And the magnitude is not relatively high, almost 5, but usually less than 5, 4 point. And mostly you can see along the fault zone. From the south, crossing into even the north in the Gulf of Thailand. And when we showed the data from our earlier research work in 2004 and 5, that was something new, that actually we have to label our main fault zones in southern Thailand to be active, which has certain implications for development and construction. But it was pretty clear that the fault zones are active. In Phuket, also later, we had, especially in 2012, I will come back, we had a number of earthquakes in a very short time, also related geographically and from the location to the fault zones. However, most of the earthquakes are relatively shallow, less than about 20 kilometers, which is also expected from the rheology. If we go to Western Malaysia, we have only about 3 historical earthquakes. And as I said, the overall number is relatively low. Here we have from 2020 and 1927. So this is more than 100 years ago. Now let us look at the data from Western Malaysia. Here in yellow again, the shallow ones. And we have a little bit blue, deeper earthquakes, and some purple and red, also quite deeper earthquakes. And again in blue, the fault zone. You also can see that some of them are related to fault zone, some of them are not necessarily related to fault zone. But if we look at the Bukit Tinggi area and the earthquakes from 2007 to 2009, we can see there's some relationship. And some of the events might be strike slip faults, but there's also a certain uncertainty here in the data. So this might be not a clear correlation, but this also depends that probably not all the fault zones are well recognized and studied because of the assumption that there is a low seismicity. But again, we have seismic events, we have earthquakes, also again, as I said, at different depths. We have one deeper earthquake in west of the, which is not shown here, but west of the peninsula, we have a very deep earthquake. And these are tomographic data, seismic tomographic data from our Chinese colleagues here in 2019. And they see that this is our subducting slab of the subduction zone. But there might be also some slab parts detached or in what way ever detached and making or providing possible rheological environments which can produce also earthquakes. So here there is an indication that even the subduction zone further away from Western Malaysia might still provide some earthquake sources due to detached slab material, which is in blue because the velocity is higher, because it's colder, it's harder than the environment surrounding it. That's why the P-wave velocity here is higher. That is a normal phenomena at subduction zones. Here under the volcano area in Sumatra, the velocities are lower because the magma is lower density and lower velocity. Now let me come to some other phenomena which we observed and coming back to the earthquakes in Phuket. But first, a short thing about earthquake sequences. We usually have main shock and aftershock. Then we have foreshock, main shock, aftershocks, and we have something we call earthquake swarms. Main shock, aftershock, I think there was a discussion in Turkey, because in Turkey we have actually two main shocks because they are on different fault. And this is one of the criteria that aftershocks have to be on the different fault, on the same fault in the rupture area. Let us look at earthquake swarms. They have relatively small to moderate earthquakes. They have the high magnitude event, and this is something very unusual. It happens later. It's not like the main shock order here. And mostly at shallow depths. And usually there are a large number of earthquakes. Yeah. There's some parameter, some criteria in terms of daily number of earthquakes per day, which might be characteristic for a swarm. And also there is the skewness and kurtosis of the energy released can be characterized with certain values. Sorry. And this is actually our Phuket earthquake from 2012. And we can see here on the left side the time and the number of earthquakes per day. And here on the right side, the cumulative number of earthquakes. You can see here that very fast and then a little bit later, less number of earthquakes occurred. The main magnitude was later. The main magnitude was here later. The main magnitude was in this area. The parameter actually defined that this is a swarm. And this is pretty clear. And you can see this is from 16th of April here to 20th of April, but mostly in 16 in one day, actually in a very short time duration, most of the earthquakes happen. We have here up to about more than 40 earthquakes. We have things like this in 2007, 2009 in Bukit Tinggi, which is especially in 2007-8. Although the time is longer, it's also, we can see here in a relatively short time, a lot of earthquakes. And later, maybe this is not really, but it can be also associated because after that there's almost no seismicity. The parameter actually identified as a mini swarm. And if you compare that, our Phuket earthquake is definitely an earthquake swarm and also a earthquake mini swarm for our Western Malaysian numbers. Let us look what is the relationship between our earthquakes and our local tectonics. The main thing is we have our fault zones, and in Thailand, definitely the fault zones are the main active earthquake producing structures. They are not necessarily specifically along the fault zones, but also distributed. Especially after the 2004 earthquake, we also contribute a number of earthquakes to the extension of the lithospheric plate. In red are hot springs. In red diamonds are the hot springs. Some of them, not all, and some of them are clearly related to our structural faults. This is different evidence is indicating that one. So here also one of the reasons and motivation that the fault zones and the hot springs somehow have a relation. And without going further into detail, also the earthquake swarm in Phuket in 2012 also is very likely related to moving hot or geothermal fluids in the subsurface, which is often an indication. Similar in Western Malaysia, the number of earthquakes is not so high, so there is not a really good correlation, as I said, except here in the area of Kuala Lumpur and north of it, Bukit Tinggi. Also the hot springs in red, can be a correlation, yes. Also, especially in this southern area, a lot of hot springs and a lot of earthquakes. So I think there will be more and further work will come on that area in the coming future. Because this is probably also, when I talk about the next topic, one of the promising areas for geothermal energy. Let us look a little bit on the regional scale. And here on the top is the number of earthquakes in green here, and also the time on the x-axis, and also the GPS displacement for the north-south in purple and the east-west in orange. Our 26 December 2004 earthquake definitely changed the plate movement. This is, I think, well known that the plate moved to the west and also to the south. That means we are going down here. But also, if we look at the Phuket swarm in 2012, we will see that shortly before was the major duplex of magnitude 8.6 and 8.2 in the East Indian Ocean. This is further on the here on this area. So this affect also the seismicity and also the plate motion direction is changing now back to north and to east. So here we get indications, and we are seeing this, and others are also working on that the larger earthquakes in the Indian Ocean in 2012 have an effect on our peninsula with a Phuket swarm and also with a change in movement. So here we can conclude that yes, we might not have so many earthquakes, but we are affected by big earthquakes in the Andaman Sea, directly, indirectly. And I think that's one of the major motivations to look further into this research direction. So what about hot springs? I talked about hot springs already, and I try not to take much of your time. Here I will focus mainly on Thailand, especially southern Thailand, because we are not working on hot springs in Malaysia. My colleagues are doing this, and a number of people are very active on that in Malaysia. Hot springs, we know this from northern Thailand here down to southern Thailand with different very hot exit temperatures in blue, especially in the north, a few in the south, then a red between 80 and 90 degree. Here in the south we have a number, and mostly they are below 40 degree, 40 to 80 degree here in green, also in the north. Here's a gap between north and the south. Here's a gap, no hot spring here. So our main area is basically here. A short note, in the northeast there are no hot springs because of the different geology. Associated and relevant is the heat flow here in the background. I will show this here again. Here we see the map here with Thailand and also our peninsula here. And we can see that actually in the south, in Malaysian, Western Malaysian area, also in Singapore, the heat flow is much higher than what we see in southern Thailand. But still we have exit temperatures of up to 80, 90 degrees. In Thailand, we already utilize the geothermal energy in northern Thailand, here in Phang. Go back. Now, Phang is here in the northern part near the border to Myanmar. And since 1988, we have this small scale 300 kilowatt geothermal power station utilizing binary technology. That means we actually have a secondary fluid which is with a low boiling point heating up, and then this secondary fluid is heating up the water for the turbine generating steam. This is running since 1988. It's still running today, so it's still working. Focusing a little bit more on Thailand, here is areas with the main hot springs for the different provinces here, from Phang Nga, Krabi, Trang, Yala here already at the border to Malaysia, here in Patalung, also in Suratani. Here exit temperatures maximum here 75, 70 here up to 80. As I told you, many of the hot springs, a number of the hot springs are related to the fault zone in the upper northern part of the southern Thailand. A few pictures and photos here in Ranong, Suratani, here very often in the river system here in Phang Nga, here in Krabi, here you can see in Trang and Yala already utilized for spa and recreation, which is the main application. We have basically 3 settings. We can separate in a more granitic setting, where the igneous rock is a majority between the heat source and the surface. We have a little bit sedimentary rock and sediments. Usually in this setting, a fault zone will provide the pathway where the cool water is going down and heated up and then moving up again. We usually see a very small number of very discrete hot springs, and the temperature is usually much higher in the upper part of the temperature range. Whereas when we have a larger sedimentary cover between the heat source and the surface, we see the similar thing, but we see more mixing at the near surface, and we see also more smaller and diverting hot springs. So not only one major, so you can see a number of smaller hot springs in the certain defined area. And number 3 is our hot springs related to the major fault zones I talked about. This is our main framework and work plan to look into the whole story. So if we start here in the middle, the main thing is basically the hot spring as a surface expression, the fluid pathway from the depths and the heat source. This is all characterizing the geothermal reservoir here and the geothermal system, which we actually can utilize here on the right side. We are also working somehow on the energy side, but it's not our topic today. Let us focus on the left side. We are applying geology, geophysics, and geochemical methodologies, here a variety, in order to understand the system by looking at the stratigraphic setting, the hydrothermal alterated rocks, fractures and faults, fluid distribution, crust, igneous bodies, and other things in order to characterize the geothermal system. An example here from Phang Nga. Here, this is a fault-related, although it's not very close, it's a fault-related hot spring in the granitic setting. Here is the geology. Here's the granite here just at the border, a little bit in the Carboniferous Permian sediments and along a river. Here's the river, and here you go, and you can see in the river we have a number of hot springs coming out, but they are all related to one system. Maximum exit temperature is here about 78 degrees. We looked at the geology and also here at the aeromagnetics, and we could identify that actually the hot spring is at the boundary of 3 igneous bodies, which cannot be separated from the geology, but can be separated from the magnetic susceptibility from the aeromagnetic. And we also did some magnetic telluric here at different depths from here 25 to 2000 meters. The light color indicate conductive areas, where the darker colors indicate resistive areas. And you can see if we are in the shallow, we have shallow distribution of sediments, water saturated. If we go deeper, we can see the conductive areas are very limited and almost going down to the 2000 meter. And these are basically our pathways from the depths to the surface of the hot water. We did also some near surface geophysical investigation here in terms of resistivity to identify the water and hard rock distribution here, the hard rock in red with high resistivity and the water here with low resistivity in blue color. And then we identify, making a schematic drawing, that we have in the valley of the river the quaternary sediments here, which are partly saturated, and the hot water is coming along one of the fractures, which is also part of the valley, making the granite is a little bit in the vicinity, not far, about 500, 600 meters away. For the larger picture, larger understanding, this is our fault zone here, the Clong-Marie fault zone, and previous investigations have identified this as a flower structure here, and you can see the granites are actually moved up along the fault zone, and also these faults are actually utilized by the water to go down and to heat up at depths. We don't know where the hot water is getting heated up, so the heat source is not known, and then the hot water is coming up. So here we see that the origin and the structure and the location of the hot spring is clearly fault related. Looking at another example further on the western side, this is in Krabi, south of Phuket, very close to the estuary system of the Andaman Sea here. And this is a saline hot spring in fractured sandstone. The salinity of the hot water is about 21 ppt, and the exit temperature is only 46. And you can see this is already utilized for spa and recreational activities. We did also a lot of investigations, but mainly in the shallow part. From resistivity, you also can see again in blue the conductive water containing layers. We cannot identify hot water, but we can identify here very clear the saline water with a low resistivity in blue. And the red one is a sandstone, which is also by seismic data, shallow seismic data. You can see relatively strong fractured, which is also identified by well cutting data. Also, we applied SB in order to identify the different locations of possible hot spring at shallow depths. And we can see here that the different flow of hot water. Hot water here is coming out on the right side, HW hot water. Here also coming out, producing clear negative SB.
Masa majori lek tu, kawin dah. Simple sangat ni. Lek dia. Tulis lah tu.
I hear something. Okay. And the hot spring is also with a number of small hot springs. That's what I outlined earlier in the sedimentary area. And we can see here the estuary is coming. So here we believe, this is a schematic drawing, that actually the hot water is coming up along the fold and mixing somehow at depths. This is not at scale here, at depths where it's mixing, can be also deeper, and then mixing and coming up as saline hot water. And also we have near the area, near the estuary, we have clay layers also on the surface, like as a sealing this aquifer, this kind of hot aquifer, and also on some discrete areas, the hot water is coming out. Because, going back, sorry, this is actually our salt marsh, so this is seasonally flooded. That means we also have clay. This is actually relatively near the beach, if we can say like that, although most of the area is covered by mangrove. So this is our idea. We have good understanding in the shallow part. We don't have data from the deeper part yet, but we have also a number of well data confirming our shallow geophysical investigations. We also did something to look into the future. We wanted to see what is happening to the system when there is artificially discharge through wells, because there is a question of how to utilize the hot spring. If we actually take a lot of water out, is this affecting our hot spring? So we actually did some flow and heat simulation with the first question to develop a steady state model, and then also showing and investigating whether there is an effect on the hot spring when there is a large discharge. So basically, this is our simulation framework. From the shallow and the deeper surface, we get the information from our geoscientific investigation. We make a geological model looking at the grid, boundary condition, initial conditions, making the simulation steps and the output. And we need to input our physical properties in order to get our steady state model. That means, can we explain what we see today? And later we add some well discharge. We basically use our GMAT, simulation for heat and mass transport, which is available. And here you can see some of our initial conditions with recharge, flux from the hot water, and discharge, and the different layers of sandstone, whether it's sandstone and sand, at the area here of 6 times 7 kilometers. And this is our results. So we can see that from a depth about 450 meters, you can see the hot water is coming very discreetly to the surface and flowing up. This here on the left side is the ocean. And we are reaching the temperature as expected, about 46 degrees Celsius. And you can see it's getting hotter with the depths. This is the east-west or the west-east. And now we are looking at the well discharge. When we add some wells with different depths and different discharge rate, what is actually happening. And you can see when we have a 25-meter depth well with about 2.6 cubic meter per hour, we can see that there is a deviation of the hot water moving to the well. If we go deeper and if we increase the discharge, it's more pronounced, especially also at depth. And later, when we discharge a lot, the hot water is mainly going to the well and not anymore going to the hot spring. So my final picture and photo actually is from Phang again in northern Thailand. This is where the geothermal power plant is actually located in next to a national park. So geothermal energy and national park are very beautiful coexisting in northern Thailand. And I think this is also a good role model for other places here in Peninsula Thailand if we want to utilize more and more our geothermal energy for the future, addressing our climate change crisis. Now, thank you for your attention. And for this one, I would stop my presentation.
All right. Thank you, Dr. Helmut, for the very insightful sharing on the earthquakes and geothermal resources of Malay Peninsula. And so for the audience, if you have any question that you'd like to ask Dr. Helmut or us, you may do so by turning on your mic or typing your question in the chat box. We will now open for the Q&A session.
So seemingly nobody would like to ask something.
Yeah, we still have another like 15 minutes.
Yes, okay, we have time. I'm
Discuss.
available. Don't worry.
Yeah. All right. Okay. So, well, in the meantime, Doctor, do you have anything that you would like to add from your presentation just now?
I'm so far fine.
Okay. Right, so from the audience, do you have any question for Doctor? All right. If that's so, Doctor, I actually have one question for you.
Yeah, sure. You're welcome.
Okay, so regarding your presentation just now, I heard that you mentioned about that you have applied this geochemical method, right, for the earthquake investigation. Can you explain like in brief details on what kind of the geochemical method that you use for this investigation actually?
You refer to our geochemical
Okay.
method in hot spring investigation,
Okay.
because we are dealing with hot water.
Okay.
But the hot water has a history, and the chemistry actually tells us the history of the hot water, and the history means where is the water going, because the water is always interacting, talking to the rocks, I can say like that. No? So, and on the way when talking, they are taking something with you. So when you make a journey, you take something with you. And we are looking at what the water is taking with us when it comes back to the surface, and what these kind of things the water take with it gives us information. So what I'm talking about is that the water is interacting with the rocks, exchanging chemical elements, and these elements going into the water, and they give us information about the depths and the temperature at depths. They can give us information about what types of rock, what happened, how long the water is. So example, we are using cation and anion to identify the equilibrium temperature. That means what is the temperature at depths where the water is coming from, or a better reservoir temperature. There's standard technology in terms of geothermal thermometers, which are well known and applied in many areas. So this is a very special, very normal cation anion. We are also using isotopes in order to see is this meteoric water? Is this water coming from the upper mantle? We also utilize modern chemistry like CFC. This is one of the greenhouse gases also used in refrigerators, but is phasing out now, which is very stable in the atmosphere. And this can also give us some information how long the water is actually in the system, because most of the hot springs are usually recharged by the rainwater, meteoric rainwater. And when the rainwater contaminated with CFC is going into the ground and then coming back later at the hot spring, it can tell us how long it took, because the concentration of the CFC is changing in the atmosphere over time, but not in the subsurface, not in the water system. So we are trying to utilize different techniques. Also, maybe one last example is that we also utilize chemistry of the gas. When there's gas coming out from the hot spring, we can analyze the gas and also can see via the isotope what is the source of the gas. Is this usually from upper mantle or not? So to answer your question.
Okay, hello everyone. Can you hear me, Doctor?
Very well.
Okay, thank you. I'm sorry, I couldn't follow the whole presentation. I actually joined late. So, but since there are not many questions and we have time, so I thought to ask you a related question. I'm Kazi Suhail, and I recently completed my PhD from UTP, and I did reservoir modeling using QI techniques in Malay Basin. So I wanted to ask, like, that was a more like, I'm a geophysicist, so reservoir characterization and reservoir modeling was my objective to be achieved during my PhD. So I would like to ask, like, in Malay Basin, how can I extend this reservoir modeling, the static model I created? Of course, the static model is something, which gives you insight about the subsurface, and the geothermal and CO2 storage sites and everything is also, more related to the, of course, subsurface. So how can I extend my study, to be utilized for these subjects like geothermal and CO2 in Malay Basin? If you could just comment, what more should I do, incorporate in my study in order to explore the CO2 sites and more like utilize it, this static model which I created up in the Malay Basin, to actually to know the geothermal sites and CO2 storage sites. Thank you. I hope I tried to clarify what I wanted to ask. Thank you.
Yes, this is something, especially in the industry, is working also in terms of energy transition. How actually in the petroleum industry we can utilize, or what is our contribution in the industry to the energy transition? Because in petroleum industry the petroleum industry working on subsurface, they have the same technologies and also similar but not the same aims and objectives. To your question, there's two things. The one is the CO2 storage, which is possible, and I think we will see more and more applications. I think the one recently now is starting in the North Sea somewhere in the Netherlands, if I remember that, where you need to look at formations where you actually can keep the CO2 for a very long time, or you maybe, like in a reservoir, keep the CO2, plug it, and maybe if you need it later, you can utilize it again as a resource, because CO2 is not necessarily only a greenhouse gas, but it's also a resource for many applications. But on the other side, CO2 is like the natural gas. It's also a gas, so it's a similar behavior, but still you have to look at the properties of CO2. How does it work? And for the geothermal, we know that the South China Sea, also here in our Gulf of Thailand, we have relatively high heat float. We have very high geothermal gradients there, or relatively higher geothermal gradients. So question is this possible in petroleum industry to utilize existing structure and wells and understanding in order to use the hot fluids, not looking at gas or oil, but looking at the hot fluids in order to, so shifting the objective not to the gas and to the petroleum, to the hydrocarbon, but shifting to the fluids, which we usually don't want in petroleum, because that means no hydrocarbon. Shifting that to the fluids and look where are the fluids rather than the petroleum, and how can we utilize it. So that means we have to look at below the oil-water contact, gas-water contact, and then looking what possible temperatures we achieve. This is, we can see also from the hydrocarbon maturity and other parameters. So shifting a little bit the objective and then utilizing the understanding and maybe looking at new data in order to answer these questions. So this is probably for you. There's a lot of development going on now in this kind of work.
All right, Doctor, thank you.
All right. Okay. Thank you, Doctor, for your explanation just now for the questions. Is there any more questions? Assume if there is no more question, then I would say that that would be the end of our 10th Geophysics webinar series. And therefore, I would like to thank Dr. Hamad Rust so much for becoming our honorable speaker for today. I believe that all of us have gained so much new and valuable insights and inputs from your sharing just now. And so before we end our session today, just a kind reminder for all of the audience, please kindly fill in the attendance Google form of this webinar in the link via the link that I've shared with you in the chat box just now. And so that is all from me. Thank you again. Thank you so much, Dr. Helmut Duras, and all of the audience. I hope to see all of you again. And with that, Assalamualaikum and goodbye from me. Thank you.
Yeah, thank you too for your part here and having me here. Thank you very much.
Thank you, Doctor.
Thank you.